Hello viewers, I welcome you all for the session on chromatography module 3. In our previous modules, we have discussed about the basics of chromatography, how the separations are going to be performed by using chromatographic techniques, the role of stationary phase, mobile phase, and how the analytes are going to interact with the stationary phase during the separation process. All these things we have discussed, and we have understood about the classification of chromatographic techniques, how the chromatographic techniques are classified based on the nature of the mobile phase. If the mobile phase is liquid, that is liquid chromatography. If the mobile phase is gaseous, it is gas chromatography. If the mobile phase is supercritical fluid, it is supercritical fluid chromatography. And all these things will be coming under column chromatography. Apart from column chromatographic technique, there is planar chromatographic technique also. So in the planar chromatographic technique, stationary phase will be poured over a flat surface, over a plane surface, and a sample is spotted over the stationary phase, and dependent upon the relative migration of the solutes, the solute molecule will move along with the mobile phase when the stationary phase along with the sample is immersed into the mobile phase which is present in a container. We will discuss more about planar chromatography when we come to thin layer chromatography. In this particular module, we will discuss about some general equations and general characteristics while performing chromatographic separation, which are very, very essential and widely used to determine the characteristics of column and the solute characteristics, etc. Right. First, let us take on what is the relationship between the retention time and the partition ratio or partition coefficient or distribution constant. You take any chromatographic technique, the separation process which is involved in the chromatographic separation process is fundamentally due to the interaction between the solute and the stationary phase. And we know from the chromatogram of the chromatographic separation what we obtain. The retention time is defined as it is the time taken by the solute to reach the detector once the sample is introduced at the head of the chromatographic column. So the retention time is a solute characteristic. Even you have understood in our previous module that from the chromatogram we will be able to obtain the identity of the solute and the concentration of the solute present in the sample solution. So these are usually obtained by the relative positioning of the chromatographic peak in the chromatogram and the height of the chromatographic peak. What we have, we can certainly obtain the identity and the concentration. I also know the distribution ratio or partition coefficient or partition ratio, just like in liquid-liquid extraction or solid phase extraction. In chromatography, distribution ratio can be defined as it is the ratio of the concentration of the solute in the stationary phase to concentration of the solute in the mobile phase. Because here the diffusion of the solute will be taking place from the mobile phase to stationary phase because the mobile phase will be used as a solvent to dissolve the sample. When the sample is introduced to the chromatographic column, solutes will show their relative migration along with the mobile phase. And this relative migration will be rapid, of course, for all those solutes which are not having any affinity towards the stationary phase. And all those solutes which are having greater affinity towards the stationary phase will show greater residence time in the chromatographic column, and therefore their retention time will be more. So you have understood from this, roughly we can say all those solutes which are not retained by the column or which are not retained by the stationary phase, they will be eluted very rapidly and they will move almost along with the mobile phase uh, in just without having any difference with respect to their velocity when compared to mobile phase velocity. Therefore, the relationships between the time taken by the solute to get eluted out of the chromatographic column and their equilibrium relationship when they are involved in the separation process, it is very important to understand. Now, to relate the rate of migration of solute, with its distribution constant, we have to express the rate as a fraction of the velocity of the mobile phase, because the mobile phase will be moving through the chromatographic column at certain speed and or at certain flow rate. So any chromatographic separation you take, the flow rate of the mobile phase is very important to be adjusted at an optimum level. Therefore, whenever the mobile phase is moving through the chromatographic column, even it will not only move but also it will take the solute molecules along with that, of course, at different time intervals. So, if you assume, as we know, V is the linear velocity of the solute which is moving through the chromatographic column, that is denoted by the equation V is equal to L by Tr, where L is the distance traveled by the solute or the length of the column what we take in the chromatographic separation process, and Tr is the time taken by the solute, or it is the retention time of the solute to reach the detector after the introduction of the sample to the chromatographic column. So how this V and U bar, this is the average linear velocity of the species present in the mobile phase, or the linear migration of the mobile phase which is moving through the chromatographic column. You also know that is denoted by U bar, and U bar can be written as L by Tm, where L is also the length of the column and Tm is the time taken by the mobile phase to reach the detector once the elution process is started. So in the chromatogram, you will be having a smallest peak, and in the smallest peak, a TM can be obtained, and that TM is known as dead time or void time. So U bar can be written as L by Tm. Therefore, what is the relationship existing between the linear velocity of the solute which is moving through the chromatographic column and the average linear velocity of the mobile phase species which is also moving through the chromatographic column during the separation process? That can be written as V is equal to U bar into fraction of time solute spent in mobile phase, because whichever the solute we will introduce into the chromatographic column, that should be obviously spending the time in the mobile phase, because the mobile phase is the carrier to carry these solute molecules out of the chromatographic column during the elution step. Therefore, the solute will be moving along with the speed the mobile phase is moving. All those solutes which are not being retained by the stationary phase will be moving along with the mobile phase with almost the same speed as the mobile phase is moving. Therefore, the linear velocity of the solute which is moving through the chromatographic column can be written as U bar into fraction of time solute spent in mobile phase. If you simplify this, V is equal to U bar into, we can write the fraction of solute spent in mobile phase, means when you introduce the sample, to the chromatographic column, sample will be distributed itself into stationary phase as well as mobile phase. So its total concentration is Ct and Vt. Say we can say out of total concentration of the solute, whatever the volume, say total volume, let it be TmL, and the total concentration is Ct molar. Then the concentration of the solute distributed to mobile phase is Cm of volume Vm, and the solute concentration in the stationary phase is Cs of volume Vs. So the total concentration will be Cm into Vm plus Cs into Vs. We know this. So what is the solute amount in the mobile phase? What is the solute amount in the mobile phase? That can be written as moles of solute in mobile phase divided by total moles of solute. So total some moles of solute has been introduced at the head of the chromatographic column, out of which some moles of the solute as transport into mobile phase, because this solute might have showed very weak interaction with the stationary phase or almost no interaction with the stationary phase. Therefore, that kind of solute will be spending the time in the mobile phase. And even for all those solutes which are also having greater affinity towards the stationary phase, they will also at one particular stage coming to the mobile phase. Therefore, the moles of solute in mobile phase divided by total moles of solute. This is the total moles of solute which is present in the mobile phase. So out of total moles of solute, this many moles of solute which is present in the mobile phase They are moving with the speed of u bar, with the speed of u bar. Therefore, V is equal to u bar into moles of solute in the mobile phase can be written as concentration of the solute in the mobile phase into volume of the solute or volume of the mobile phase, concentration of the solute in the mobile phase into volume of the mobile phase divided by total moles of the solute. As I told you, that is the summation of moles of solute in the stationary phase to moles of solute in the mobile phase, that is denoted by C into V, Cs into Vs plus Cm into Vm. So if you simplify this, U bar into, if you take Cm into Vm as a common factor, Cm into Vm as a common factor, if you take, that will be giving you for this particular term 1 over Cs into Vs divided by Cm into Vm plus 1. Therefore, Cm into Vm divided by Cm into Vm will be getting cancelled, and at the end you will be left with V is equal to U bar into 1 over 1 plus Cs into Vs divided by Cm into Vm. We know from the equilibrium principle that the partition ratio or the distribution ratio or partition coefficient during the chromatographic separation for the selective transfer of the solute from mobile phase to the stationary phase is denoted by the equilibrium constant, that is K, which is simply the ratio of the concentration of the solute in the stationary phase to concentration of the solute in the mobile phase. So if you substitute this value here, K is equal to Cs divided by Cm. So Cs divided by Cm is here. In place of Cs divided by Cm, if you put K, you will be ending up with V is equal to U bar into 1 over 1 plus K into Vs divided by Vm, where K is the distribution ratio or partition coefficient. So the final equation we will get it as V is equal to U bar into 1 over 1 plus K into Vs by Vm. So the linear velocity of the solute which is moving through the chromatographic column is not only dependent upon the partition coefficient of that, but also what is the volume of the stationary phase present in the column and what is the volume of the mobile phase which is moving through the chromatographic column. It is also very important. So suitable volumes of the stationary phase and mobile phases have to be chosen whenever we are preferring to separate some kind of solutes by using column chromatography technique. So according to the column parameters, we may have to use suitable volumes of stationary phase and mobile phase in order to achieve adequate separation. So therefore, this is a very important equation to relate the linear velocity of the solute which is moving through the chromatographic column and the average linear velocity of the mobile phase which is moving through the column and the partition coefficient. So this equation describes the relative migration of the solute and that of the mobile phase through the chromatographic column. All right. So one more important factor is the retention factor. Retention factor is also known as capacity factor, which is denoted by lowercase k or k dash. This retention factor is a solute characteristic with respect to the column. So this value of K will be different from one column to another column. So whatever the solute you are separating, you have to calculate the capacity factor or retention factor. Based on the capacity factor or retention factor value, we will be in a position to decide whether the separation process is taking place faster or slower, or is the separation feasible or not. We can decide by means of this retention factor value or capacity factor value, that is K or K dash. So what is this? This is an important experimental quantity and which is widely used to compare the migration rates of solutes in the columns, as I told you, at what speed the solute is moving, whether the solute movement is rapid. If the solute movement is rapid, means that particular solute will not show any affinity towards the stationary phase. Therefore, it will be moving through the chromatographic column along with the mobile phase. So as soon as the mobile phase peak is eluted out, if there is a spike in the chromatogram, and that is definitely for the solute which has not shown any interaction with the stationary phase. Therefore, what is the migration rate of the solute through the chromatographic column? We can understand if the value of K is larger, The relative affinity of the solute towards the stationary phase is more. If the value of K is smaller, there is a rapid elution of the solute is possible. So these are the two factors we can make use of this capacity factor or retention factor in order to understand or in order to compare the migration rates of the solutes in the columns. So let me say this retention factor, capacity factor is a solute characteristic, as I told earlier. And if we assume solute A, there is only one kind of solute is present in a typical sample which you are going to subject for the separation process. And the retention factor or the capacity factor for that particular solute A will be denoted by Ka or Ka dash. So you capital Ka means this is the partition coefficient for solute A. Small ka means it is the capacity factor or retention factor for solute A. And this can be defined as you have the previous expression here V is equal to U bar into 1 over 1 plus K into Vs divided by Vm. And this K into Vs divided by Vm, you will be getting the retention factor, capacity factor. So the retention factor or capacity factor is dependent on the partition coefficient also. If the partition coefficient is more, the retention factor or capacity factor will also become more. That means to say that whenever the partition coefficient value become larger, that means to say that the solute affinity towards the stationary phase is more, and there is a greater migration of the solute towards the stationary phase has been achieved. Therefore, the value of Ka become very high, right? So the capacity factor Ka or Ka dash is equal to Ka into Vs divided by Vm, where Ka is the distribution constant of solute A. And similarly for solute B, solute X, solute 1, solute 2, you can write Kb, Kx, Ky, K1, etc. to write the capacity factor expression. So if you substitute this into the previous expression, what I have presented in the previous slide, you will get V is equal to U bar into 1 over 1 plus Ka, because in place of Ka into Vs divided by Vm, you will substitute the value of Ka. So V is equal to U bar into 1 over 1 plus Ka. We know that V is equal to L by Tr and U bar is equal to L by Tm. The relationship between the velocity of the solute along with the mobile phase and the time taken by the solute to reach the detector, that is the expression is V is equal to L by Tr, and the average linear velocity of the mobile phase which is moving through the chromatographic column to travel the distance L centimeter or L meter is U bar is equal to L by Tm. So you bring these two, V is equal to L by Tr and U bar is equal to L by Tm into this particular equation. In place of V, if you put L by Tr, and in place of U bar, if you put L by Tm, you will get L by Tr is equal to L by Tm into 1 over 1 plus Ka or 1 over 1 plus Ka dash, right? So L and L will be getting cancelled because LHS and RHS, they are commonly having this term L. So 1 by Tr is equal to 1 by Tm into 1 over 1 plus Ka, or if you further simplify this for Ka value, you will be getting Ka is equal to Tr minus Tm divided by Tm, or K dash is equal to Tr minus Tm divided by Tm. So this is the equation which is very useful to calculate the capacity factor of any solute, where subscript A indicating the solute A, if subscript is 1, that is going to be solute 1. So Ka is equal to Tr minus Tm divided by Tm, where Tr is the retention time and Tm is the void time, and this Tm is also dead time or void time. And these two values, these two parameters can be readily obtained from the chromatogram. So if you have the chromatogram, we can easily calculate the capacity factor value. We can easily calculate the value of retention factor for any kind of solute which has been separated by the chromatographic technique. So this is a very important expression which is used to calculate the retention factor or capacity factor for any kind of solute. So if you further simplify this, we know the difference between the retention time and the dead time is the adjusted retention time, that is denoted by Ts, or it is also denoted by Tr dash. So Ka is equal to either Tr minus Tm by Tm or Tr dash divided by Tm or Ts divided by Tm, where Tr dash is the adjusted retention time. This adjusted or corrected retention time is nothing but it is the time taken by the solute to stay in the stationary phase. How long the solute has stayed in the stationary phase, that is adjusted retention time. The particular typical residence time of the solute stayed in the stationary phase is known as adjusted retention time. Retention time means it is the time taken by the solute to reach the detector once the sample is introduced to the chromatographic column. So they are different. So you have to subtract Tm from retention time to get adjusted retention time. So Ka is equal to either Tr minus Tm divided by Tm or Tr dash divided by Tm. Therefore, if we have the chromatogram, these parameters can be obtained and you can calculate the capacity factor value. If the capacity factor retention factor value is less than unity, what does that means? If the capacity factor or retention factor value is less than unity, that means to say that the solute is going to be eluted rapidly, means that particular solute will be coming out of the chromatographic column almost along with the mobile phase. When you introduce the mobile phase at the end of the at the head of the chromatographic column to initiate the elution process, during the elution stage, the mobile phase peak will be obtaining. If the value of K is less than 1 for any solute, means there is a peak almost close to the mobile phase peak. So that solute is going to emerge very rapidly. So the time taken by that particular solute will be almost the same as void time or dead time. So if the value of K is less than 1 for any particular solute, the retention time for that particular solute will be almost the same as dead time, right? So the rapid elution of the solute taking place if the value of K is known as less than 1. If the value of capacity factor is greater than 20 to 30, then definitely the retention time for that solute going to be inordinately long. Means that solute is having greater interaction with the stationary phase and there is zone spreading while forming the band in the chromatographic column and that solute is not ready to come out as early as possible. So it is having, we can say sometimes some solutes will show irreversible interaction with the stationary phase and we may have to play in order to violate that irreversible interaction of the solute with the stationary phase and to get eluted. Therefore, if the retention time is longer, then definitely the capacity factor value will be in the range from 20 to 30. So therefore, it is very important to adjust the chromatographic conditions in such a way that the capacity factor or retention factor should be ranged in between 1 and 10. So the capacity factor should be neither less than 1 nor greater than 10. In such a way, you have to fix the experimental condition. So how to do this? So say for example, in liquid chromatography, you will be using different columns, I mean to say different stationary phases and the mobile phase as usual you will be using. And the capacity factor value can be adjusted by adequate selection of the column packing, that is the stationary phase. So you have to optimize the stationary phase condition. You have to use a suitable stationary phase in order to obtain the capacity factor at a reasonable value. Therefore, the change in the column packing will yield the required capacity factor value or retention factor value. And even in liquid chromatography, we can change the mobile phase composition to change the capacity factor value. If you change the mobile phase composition or the elution power of the solvent, which is used as a eluent, then the retention factor or capacity factor value can be made lesser. So this is how in liquid chromatography the capacity factor value will be adjusted. And even in gas chromatography, same thing is holds good, but we will not play anything with the mobile phase because the mobile phase will be gaseous in nature in gas chromatography. But we can play with the packing material. We can change the column packing in order to adjust the capacity factor or retention factor value. So therefore, The optimization of the chromatographic conditions is very important in order to get the capacity factor value between 1 and 10. So we should not ignore if the capacity factor is less than 1 or greater than 20 to 30, because if the capacity factor value is less than 1, the solute is going to be rapidly eluted, and we will not be in a position to obtain the solute characteristics from the chromatogram, and either the quantification, identification or quantification of the solute by means of that chromatogram will be impossible. Therefore, it is very, very essential to adjust the chromatographic conditions in such a way that the capacity factor value under such experimental conditions should be in between 1 and 10. It should not be it should be neither 1 less than 1 nor greater than 10. In such a way, you have to adjust the capacity factor. So all these things we can play when we do the chromatographic separation. First, we have to fix the experimental condition by trial and error method almost, and once we feel that particular chromatographic condition suits well, then we can use it as authenticated chromatographic procedure for the separation of that solute. And another factor as a capacity factor or retention factor, which is also equally important, is selectivity factor. And this selectivity factor will describe the relative migration rate of the solute, and this selectivity factor will describe what is the selectivity of the column for the separation of the solutes when they are present together, more than one solute if present in the sample. What is the selectivity of the column, whether the column is suitable for the separation of pair of solutes they are present in the sample with more selectivity or not. So this is nothing but the selectivity factor. So selectivity factor is the other terminology which is used to express the relative migration rate of the solute, and mathematically it is denoted by alpha. So if you assume we are using a chromatographic procedure for the separation of solute A and B, then the selectivity factor or the separation factor, selectivity factor is also called as separation factor. Alpha is written as the ratio of partition coefficient of Kb divided by partition coefficient of Ka. Alpha can be written as it is the ratio of the partition coefficient of solute B to partition coefficient of solute A, where Kb and Ka are the partition coefficients of solute B and A respectively. Here, the numerator should be the partition coefficient of strongly retained species because its partition coefficient value should be larger. Whichever the solute is strongly retained by the stationary phase in the chromatographic column, the partition coefficient of that solute has to be written in the numerator. And in the denominator, the partition coefficient of the solute which is weakly retained by the stationary phase has to be written. So Kb is greater than Ka here. The partition coefficient of strongly retained species, of course, it will be greater than the partition coefficient of weakly retained species. Means where solute B is more strongly retained species by the stationary phase and it is not moving along with the mobile phase rapidly. A is going to be fast eluted species. When you introduce the solutes A and B into the chromatographic column for the separation process, and if you record the chromatogram, in the chromatogram, the first peak will be for A because it is fast eluted species. And the second peak will be solute B because it is strongly retained species. So this species will be having more residence time when compared to the residence time of solute A because solute A is moving faster and solute B is moving slowly. And also, if you rearrange this particular ratio Kb divided by Ka, you can get alpha is equal to small kb divided by small k. This is the capacity factor or the retention factor. Capacity factor or retention factor is also a term which is used to express the migration rate of the solute. Therefore, what is the relative migration of solute B and what is the migration rate of solute A we know, and you just substitute, you will get alpha is equal to Kb divided by Ka, and this is also same expression Instead of this, we can use in order to calculate the selectivity factor or separation factor for a pair of solutes when they are subjected for separation by chromatographic technique. So you have any particular column, any suitable column which is going to be used for the separation of solute B and solute A. The separation factor or selectivity factor will be simply TRB minus TM divided by TRA minus TM, because you know KB is equal to TRB minus TM divided by TM, and Ka is equal to TRA minus TM divided by TM, where TRB and TRA are the residence time or retention time of solute B and solute A respectively. So the denominators in Kb and Ka expressions will be getting cancelled. Therefore, you will be left with alpha is equal to TRB minus Tm divided by TRA minus Tm. In this equation, if you substitute alpha is equal to, in place of Kb, TRB minus Tm divided by Tm, and in place of Ka, TRA minus Tm divided by Tm, Tm will be getting cancelled, and you will be left with only TRB minus Tm divided by TRA minus Tm. And of course, these parameters are also obtained from the chromatogram. So TRB and TRA are the retention times per solute B and solute A respectively, and Tm is the void time. So by substituting these parameters, you can calculate what is the value of alpha. What is the value of alpha? Here, TRB will be greater value and TRA will be lower value. Therefore, alpha will be greater than 1. So what is the use of this alpha? This alpha value will be giving us the information about whether the column is suitable or most adequate for the separation of these pair of solutes or not. So the resolving power of the column for the separation of pairs of solute will be decided by using this value of alpha. Therefore, as important as capacity factor or retention factor, even the selectivity factor also. So these mathematical expressions are commonly employed in order to calculate the required parameters for any solute or for any group of solutes, and in order to decide whether the column is a characteristic one in order to achieve the successful separation or not, we can decide. And one more thing is resolution, column resolution. Resolution will come to the picture whenever we are in a position to separate two solutes. When we achieve separation of two solutes, when we achieve the separation of two solutes, we will have a chromatogram with two peaks. We will have chromatogram with two peaks. So whether those two peaks are well resolved, how to decide? So there are two parameters we have to look in the chromatogram. One is, are the chromatograms, are the peaks in the chromatogram are separated sufficiently? Is there any overlapping between the peaks? So these are the two factors we have to look into the chromatogram when we end the separation process. So this is explained by the column resolution denoted by RS or R. So if you have two bands in the chromatographic column, those two bands will be eluted with two peaks. So how far these two bands, right? How far these two bands with their relative widths. So this is the resolution. So the resolution denoted by R of a column tells us how far apart two bands are relative to their widths. So whether their width is appropriate and they are separated appropriately without any overlapping, that is resolution. So this resolution is a column characteristic, whether the column is suitable for the baseline resolution of two analytes, because minimum two analytes, when they are separated, then only the term resolution can be used. For eluting single analyte, this resolution will not be suitable to calculate or to express. So whenever two analytes are eluted, whether both the analytes have been separated properly, that is decided by the resolution. So the resolution for the separation of two solutes obtained by one column will be different from the resolution for the separation of two solutes obtained by the other column. Therefore, resolution is a terminology which is compared between the columns, which is compared between the columns. So you know general picture of chromatogram. Chromatogram is nothing but it is a graphical representation of the detector signal versus time. You will be getting a symmetric peak. You will be getting a symmetric peak. Symmetric peak means if you cut the peak into two equal halves, one half will be exactly mirror image of the other half. That is known as the symmetric peak. And there will be no either tail at the beginning of the chromatogram or at the end of the chromatogram. So they have to start and end symmetrically with a maximum point, And this chromatogram is a graphical representation of the detector signal. Detector signal is nothing but the detector will respond to some property of the solute characteristic versus time, versus time. So you will have a mobile phase peak. So from that we will get the value of Tm, and we will have the solute peak. From that we will get the retention time. The retention time can be obtained by interpolating the peak point to the x-axis, So that is known as retention time here. The retention time is nothing but when the sample is injected. So to reach the detector, how long it took the time, how much time it has taken to reach the detector, that is retention time. So this is usually chromatogram. So in any chromatogram, the width is also very important. So WB and W off you can see here. WB is the baseline width. W off is the width at 50% height of the chromatographic peak. This is the chromatographic peak. WB is the baseline width. W off is the height of the chromatographic peak at 50% of the overall height. Assume this is the 100% height, and you divide this into two of vertically, and at the mid if you place a measuring scale, what is the width at 50% of the chromatographic peak, that is denoted by W off. So this W off value is very important in order to calculate the resolution between the two peaks. So you should remember that the resolution value can be calculated between the two solutes, So in the chromatogram, you should have at least two peaks, If you have two peaks, for the two peaks, they are for corresponding solutes. Solute A will have retention time of TRA, and solute B will have the retention time of TRB, and solute A will have baseline width of WAB, and solute B will have baseline width of WBB. And in respect to that, the baseline width at 50% of the chromatographic peak are denoted by WA by 2 and WB by 2 for solutes A and B respectively. So this chromatogram is clearly indicating about the appearance of the mobile phase peak, appearance of the peak for solute A, and appearance of the peak for solute B, where the time taken by the mobile phase to reach the detector is Tm, and time taken by the solute A to reach the detector is TRA, and the time taken by the solute B to reach the detector is TRB. All these parameters you can get it from the chromatogram. And the baseline widths for solute A and solute B are also given here. So this is WA and this is WB. Baseline width, it is very simple. At the base of the chromatographic peak, what is the width you can measure? By putting a measuring scale, you can measure what is the width at the baseline. So WA and WB. As the baseline width is increased, definitely the capacity factor value for that solute is going to be larger. So you should remember, if the baseline width is more, the capacity factor value or retention factor value will also become longer. So as the baseline width is more, and as a consequence of the wider value of the baseline width or greater value of the baseline width, the solute is going to be eluted in longer time. So you should remember this. So the retention time for solute A and retention time for solute B, and the baseline width for solute A and the baseline width for solute B, and the baseline width at 50% height of the chromatographic peaks for solute A and B are denoted by WA by 2 and WB by 2. You know all these terminologies from the chromatogram. And how to write the resolution then? So it is written as resolution RS or R is equal to TRB minus TRA divided by WA by 2 plus WB by 2, where TRB is the time taken by the strongly retained species. TRB is the strongly retained species because its retention time will be more, and TRA is the retention time of less retained species, that is the solute which is going to be eluted first. And WA by 2 is the width at 50% height of the chromatographic peak for solute A, and WB by 2 is the width at 50% height of chromatographic peak for solute B. Right. If you simplify this, you take 2 as common value, and you will get RS is equal to, this 2 will be going to the numerator, 2 into TRB minus TRA divided by WA plus WB. WA plus WB. Here, the difference between TRB and TRA, this is going to be TRB, and from here to here, this is TRA, and you will get delta Z at delta TR. The change in retention time between solute B and solute A is denoted as delta TR and delta Z. Whichever is convenient to you, you can use. So in place of TRB and TRB minus TRA, you can put delta TR. So resolution you will be getting as 2 into delta TR divided by WA plus WB. Resolution is equal to 2 into delta TR divided by WA plus WB. So if you have a chromatogram for achieving the separation of two solutes at least, whether they are well resolved, whether their separation is adequate or not, we can decide by looking at the resolution value, by looking at the value of the resolution. So resolution can be calculated by using this expression. Delta TR is nothing but the difference between the retention time of strongly retained species and the retention time of weakly retained species. W and WB can be obtained at the baseline. So W and WB you can obtain at the baseline in the chromatogram. You can just substitute and you can have the value of RS. So this chromatographic resolution is very important, as I told earlier, in order to decide whether the solutes are getting separated without any overlapping. If there is any overlapping, means one solute is getting eluted with the other solute, then the separation is not going to be adequate. So therefore, the chromatographic conditions are set in such a way that there is no overlapping between the peaks. You can see in this particular slide how the resolution is improved. Here. Here, the peak resolution I have denoted for the separation of solutes A and B in 3 different chromatographic conditions. So you might have used 3 different columns, and in which 3 different chromatographic procedures might have been followed in order to achieve the separation of solutes A and B. So in all these 3 individual chromatographic procedures, the obtained chromatograms are presented here. So if you look at this chromatogram, in this chromatogram, there are peaks for solute A and solute B. There are peaks for solute A and solute B. They're almost overlapped. One peak for solute A is getting eluted with the peak of solute B. They are overlapped. The peaks are overlapped. Means the elution of solute A and B are taking place parallelly together. So one peak is overlapped with other peak. Therefore, the resolution is very, very low. Between solute A and B, there is no adequate separation possible. No adequate separation possible for the separation of solute A and B when you use the chromatographic procedure which was followed in getting these chromatograms. If you look at here, the degree of overlapping has been somewhat improved, reduced in this particular chromatogram. There is a peak separation. But if you look at the width at the baseline, the width for solute A is more than the width for solute B, and these peaks are not identical with respect to their widths. Of course, they have been eluted at different time intervals, but they don't have symmetric baseline widths. Therefore, Here, when compared to this particular chromatogram, this chromatogram is okay. That means to say that here the resolution has been improved when compared to the resolution achieved here, right? You come here in this particular chromatogram. This is the chromatogram obtained by the separation of solute A and B by using some other chromatographic procedure. So A and B. Other chromatographic procedure was followed in which the column was different than the columns used in this procedure and in this procedure to obtain these two chromatograms. Here, peaks are well resolved, peaks are separated, well separated with almost symmetric baseline widths WA and WB, WA and WB. So TRA you can have, TRB you can have. There is some maximum difference between TRB and TRA, and not only the different stages of elution of solute A and solute B with their characteristic retention time, but also their baseline resolution is also possible. They have not showed any greater width. The greater width leads to cause band broadening. That I will explain when I come to the aspect of band broadening. Don't worry about that here. So W and WB are almost symmetric, and the baseline resolution is possible. These two peaks are separated well, therefore the resolution is very high. So if you compare the relative positioning of the peaks and the relative overlapping of the peaks in three different chromatograms, here the resolution was very poor, here the resolution was moderate, and here the resolution is very good, very good. So, in respect to the mathematical values, we can say here also the three chromatograms have been presented. So, this is the first chromatogram for the elution of solute A and B, and this is the second chromatogram showed for the elution of solute A and B, and similarly, this is the third chromatogram. Here, the resolution is 0.75. Degree of separation of solute A and B is very less here because solute A and B are showing more overlapping. More overlapping. Peak separation has not been taken place here. Therefore resolution is only 0.75. Here the resolution is 1. Resolution is 1. Here A and B are somewhat separated, but still there is overlapping between A and B. There is no separate baseline width. They are not baseline resolved. Here it is poorly baseline resolved. Here it is moderate, we can say. So baseline resolution, baseline separation of the solutes must be possible whenever you use any chromatographic procedure. That is going to be our objective. Therefore, here the baseline resolution is very poor. Here also it is only moderate. But if you come here, solutes are going to be eluted one by one. There is a distinct retention times for both the solutes. And there are distinct baseline widths for both the solutes. So we can calculate the resolution very easily. This is going to be the retention time for solute A, and this is going to be the retention time for solute B. And the baseline widths for solute A and solute B can also be obtained from the chromatogram. And you can just substitute these values into the expression RS is equal to 2 into delta TR divided by WA plus WB, and you can calculate the value of resolution. So if you look at the values, because here the peak overlapping is more, resolution is less. Here the peak overlapping is somewhat reduced, slightly reduced when compared to here, resolution has improved. And here the resolution is extensively increased to 1.5 from 1 or 0.75. Therefore, the resolution is a very important parameter which decides whether the column is suitable for the baseline resolution of pair of solutes. So like this, the parameters such as retention factor or capacity factor and the selectivity ratio or selectivity factor or separation factor and the resolution are the three important parameters, and for which we have to understand about the mathematical expressions in order to calculate the values. And by calculating the values, we will be able to say whether the column is suitable for the separation or whether the solute is getting separated properly or not. And is there any necessity to modify the chromatographic condition? All these things are going to be decided by these parameters. So these are about some relationships. So we have discussed. So in this particular module, we have understood about what are the expressions we will use to calculate the retention factor, selectivity factor, and the resolution. So these values are very important as we understood. So I thank you for your patience. We'll see you in the next module.